Sieve tray columns are widely used in the chemical and process industries for distillation and absorption separations. The objective of this tutorial is to gain insights into vapor liquid contacting on sieve trays. This understanding is gained using computational fluid dynamics simulations. In pursuing this line of work using CFD, I have been strongly influenced by the works of Michael James Lockett, whose textbook is strongly recommended as reading material for background on sieve tray hydrodynamics. In this book, Lockett writes, distillation trays are so simple. Sieve tray decks are, after all, hardly more than sheets of metal with a few holes punched in them. This, of course, is the fascination that the behavior of something so simple can be so difficult to predict with regard to its hydrodynamic and mass transfer performance. We resort to CFD simulations not only to gain an understanding into the hydrodynamics of sieve trays, but also to investigate whether CFD simulations can be investigative tools to predict the performance of hardware configurations for which no experimental data are available. In industrial practice, the vapor liquid contacting on sieve trays can occur in a variety of flow regimes that is shown in this diagram. They range from spray regime, mixed froth regime, emulsion regime, free bubbling regime, bubbly flow regime, and the foam regime. Roughly speaking, these regimes are traversed with lowering of the vapor flow rate through the tray. So at very high vapor velocities, we have spray regimes, and at lower vapor velocities, we may be in the bubbly flow regime. Absorption columns generally operate with large weir heights in the bubbly flow regime or the free bubbling regime, because liquid residence times is important in absorption separations, whereas normal distillation columns are most likely to operate in either the spray regime or the mixed froth regime, or even the emulsion flow regimes. To gain some elementary understanding of the rise of bubbles, you can view this presentation on my YouTube channel. Most of what I'm going to present later in this presentation are probably restricted to this flow regime, but I will talk about that at the appropriate juncture. Let's first gain an understanding of how liquid flows across the tray from the inlet to the outlet. This is the inlet weir, this is the outlet weir, and we first perform CFD simulations to determine the velocity trajectories and profiles as the liquid traverses from left to right as it moves across the tray. To keep matters simple, we switch off the gas, as it were, and just consider liquid flow. And in this simulation, we assumed a two-dimensional approximation of liquid flow. In other words, the height of the liquid on the tray is just one computational cell. Let's have a look at the animation first. These are the velocity profiles shown by the arrows, and we note that the liquid moves from left to right. But what is also interesting is to note the backflow and the circulatory flow at the edges of the tray. So what really appears to happen is that the liquid shoots straight through and creates a recirculatory flow at the spherical edges. So this would suggest that these regions may be regarded as dead zones. In fact, the first publications to quantify liquid channeling effects on distillation trays and the influence on the distillation tray efficiencies were published by Kenneth Edwin Porter, Michael James Lockett, and their PhD student C.T. Lim in the early 70s. This work was carried out at the University of Manchester. They constructed a large experimental unit and placed it on the roof of the building and pumped water across the tray and used ping pong balls to track the liquid circulatory flows. These classic papers are well worth revisiting and rereading. Let's examine the dead zones a little bit further. To gain an understanding of the formation of dead zones, we do a computational experiment and inject a tracer along the inlet. This is the scale of the tracer concentration. Red is the pure tracer, 0 is pure liquid. Let's have a look. We note from this that there is tracer lingering in the spherical in the edges of the circular tray, whereas there is no tracer in this portion of the tray. Therefore, these zones may be regarded as dead zones. This is worrisome for a tray designer if this is true, because this would imply that these circular edges do not partake in exchange with the main portion of the tray. But this situation exists because we have no vapor flow through the tray. So let us ask the next question, will the dead zones persist when we introduce vapor at the bottom? We turn to a fully three-dimensional CFD simulation of gas-liquid flow on a sieve tray. Liquid flows across the tray of diameter 30 centimeters, and the vapor is injected at the bottom through 180 holes, and the vapor traverses upwards through the liquid phase. The grid used for the computations are shown here. This is the inlet weir, this is the outlet weir, and we adopt an Eulerian strategy for vapor-liquid flows, and the description of the simulation strategy is available in these publications. Let's have a look at the results of the simulations to gain some insights into how vapor and liquid phases are contacted on a sieve tray. Let's examine the results of the CFD simulations for gas and liquid flow. In our simulations, gas is air, liquid is water, and the 3D simulation results can be viewed from different angles and at different positions. We focus now on this rectangle colored red. Just to recap, this is the inlet weir, this is the outlet weir, and liquid flow is across the tray from left to right, and airflow is upwards. Have a look at these color codings, and that indicates the volume fractions of the phases. Red indicates a liquid volume fraction of 1. Blue indicates a liquid volume fraction of 0. In other words, blue is pure gas, red is pure liquid. We start the simulations with liquid on a tray, and then at time t is 0, we start the gas flow. Let's look at the gas and liquid flows at this position shown by the rectangle. We note there is a gas cap here because it's colored blue, and at the bottom of the tray there are regions where we see a lot of red, indicates that adjacent to the perforated holes on the tray we have some liquid layers there that are not aerated. This is the inlet, and we see a preponderance of liquid near the liquid inlet. And this is the liquid outlet. Again, we see colored red, indicating that there is a preponderance of liquid near the exit to the downcomer. If you look at the arrows that indicate the flow velocities, we see that the arrows are going round and round in circles, indicating that there is a mixed pool here. And if you follow the arrow here from the liquid inlet to the downcomer outlet, we see there is a velocity vector that goes in this direction that is indicated here. And the flows here, again, we have some kind of a rotational flow indicated here. So crude summary of the flow map shows two well-mixed pools, one here, one well-mixed pool here, and there is a tendency for the liquid at the bottom here to follow this trajectory. The gas liquid follows this trajectory and exits the downcomer. Let's have a different view of the gas liquid hydrodynamics on the sieve tray. We focus on the happenings in this red rectangle. This is the liquid inlet weir, outlet weir. This is the flow direction of the liquid. So we have the view from the weir, or the side view. The color code is the same as before. Red indicates pure liquid. Blue indicates pure gas. Let's have a look at the animation. We see the gas cap here and high concentration of liquid on the tray. We also note there is a higher concentration of liquid near the edges here, indicating there is some degree of stagnancy of the liquid near the edges of the tray. Now examine the velocity vectors. We see that the velocity vectors are directed upwards and then downwards, indicating this kind of a circular motion. The velocity vectors on the right show they're going upwards here and downwards here, indicating a mixed pool on the right hand side. So we have two well mixed pools, and if we combine this information with the information from the front view, we would anticipate that the tray on the whole has a total of 4 well mixed pools. Let's see if that is true by having a look at the gas liquid flow from the top of the tray. We examine the flows at a distance of 1 centimeter above the bottom of the tray, just near the vapor inlet. Just to reiterate, the color coding is the same as in the previous two slides. Red is pure liquid, blue is pure gas, and we start the CFD simulations with liquid on the tray, and at time t0 we start the gas flow. Let's have a look at the animation. We note that all velocity vectors are drawn towards the middle of the tray. You can see all these velocity vectors seem to converge in the middle. So I give you a indication of these velocity vectors. That is because this is the liquid inlet, this is the liquid outlet. The liquid is drawn towards the middle before the gas disperses the liquid upwards. You also see a preponderance of red on the edges, indicating there's some degree of stagnancy at the curved portions of the tray. So far, there's no indication of four well-mixed pools. That is because we are looking at the flows right near the bottom. We now move upwards and look at the flows at a distance of 4 centimeters from the bottom, halfway between the gas cap and the bottom of the tray. So now our focus is on the portion of the gas liquid hydrodynamics in the area indicated here in red, 4 centimeters above the bottom of the tray. Same color coding as before, and let's start the animation. If anything, the flows are even more chaotic than viewed from the front or from the weir side. And the flows are all kinds of directions. For example, if we follow the velocity vectors, we will note that they are drawn towards the edges here, and from the edges they are drawn towards the liquid outlet. Flow in the middle is directed towards the liquid outlet, but some of it returns back here. Difficult to say conclusively, but there appear to be regions which are almost circulatory in this direction here, but overall the flow is from the inlet to the outlet, but the up and down motion is restricted to 4 different regions, indicating there are 4 well-mixed pools, but you can't tell conclusively from this view. You have to examine the entire 3D flows as a whole to reach that conclusion. To quantify the liquid mixing characteristics on the sieve tray, we inject a liquid tracer at the liquid inlet here and follow its trajectory or concentration as it moves out of the tray. The red tracer has disappeared already, and there's no tracer left in the column. There are no stagnant regions because there is no red tracer in the liquid. Again, the velocity vectors indicate the two well-mixed pools concept we had already established. We now view the tracer development from the top at a distance 4 centimeters from the bottom, at this position indicated red. Let's start the tracer injection. Red is at the left, and it disperses. Across the tray. The velocity profiles are indicated here, and they also coincide naturally with the ones we had already observed previously. We now examine the gas liquid flows on a sieve tray of 90 centimeters diameter, and to see how the gas liquid flows alter with increasing scale. We examine the gas liquid flows from the front and focus on this rectangular area. The animations indicate that there are a number of well-mixed pools along the tray, and therefore as the tray diameter increases, the liquid flow on the tray can be approximated as being in plug flow. This explains several of the models used to calculate the Merfree tray efficiencies. And in practice, the Merfree tray efficiencies may exceed unity because of the staging of the liquid on the tray. Let's focus on the red rectangle here and have a weir view of the gas liquid flow on this 90 centimeter tray. This is much of the same story as before. There appears to be a number of well-mixed pools on the tray. And only at the edges near the curved portions is there some degree of stagnancy. Let's have a look at the gas liquid flow from the top at a distance 1 centimeter from the vapor inlet. As for the 30 centimeter diameter column, the liquid is drawn towards the middle and dispersed upwards by the entering vapor. But you can already distinguish several pockets where the velocities are vectors are indicative of circulatory motions, indicating the existence of a number of well-mixed pools. Let's now have a look at the happenings at a distance halfway between the vapor inlet and the vapor outlet. You can see a number of pockets that indicate a multiplicity of well-mixed pools on the tray. We have presented results of 3D Eulerian simulations that provide some insights into liquid circulations, residence time distributions, and scale effects on sieve trays. These simulations were performed for the bubbly flow regime of tray hydrodynamics. The extension to the spray regime is more challenging. Further details of a quantitative nature regarding hold-up distributions up along the height of the tray, axial dispersion modeling of the tray hydrodynamics can be found in my publications. Other aspects of sieve tray hydrodynamics will be considered in subsequent presentations.